Welcome to this video. Today we are talking about the transformers without normalization paper. It was published by the Meta team. We can see it here together with the New York University, MIT, Princeton, and it was published in the year 2025 in March. So very recently, it's just 1 month ago. So let's just start and jump into the abstract. Normalization layers are ubiquitous in modern neural networks and have long been considered essential. This work demonstrates that transformers without normalization can achieve the same or better accuracy using a remarkably simple technique. We introduce dynamic tanh. So what does it mean? They say that normally we always using normalization layers since always. So every time we are training neural networks, we implement some normalization layers. Sometimes it's like batch norm or layer norm or stuff like that. So but they are claiming that they found a way where we don't have to use a normalization layer such as LayerNorm anymore. So that's pretty interesting. And they say DIT is inspired by the observation that layer normalization in transformers often produce tanh-like S-shaped input and output mappings. So they had some observations, we will see it later in the figures, and this is why they argue that there's a way where we could replace the layer norm with this, that's the one with a function like this, where the alpha is a learnable parameter. We validate the effectiveness of transformer with DIT across diverse settings, ranging from recognition to generation, supervised to self-supervised learning, and computer vision to language models. So they're not showing that it works on MNIST, for example. Everything works on MNIST. They show that it also works on on different domain with different pre-training or training ideas. So from self-supervised learning to supervised learning, from computer vision to language, and they also showed that it works for like DNA sequences. These findings challenge the conventional understanding that normalization layers are indispensable in modern neural networks and offer new insights into their role in deep network. So I think that's a pretty big statement what they are doing here in their abstract. So let's just dive in and see if it makes sense and what they find out. Let's just jump into the introduction. Over the past decade, normalization layers have solidified their position as one of the most fundamental components of modern neural networks. It all traces back to the invention of batch normalization in 2015. So let's just have a small recap about the batch normalization and how it works. So what the authors find out is the it's called internal covariate shift. And this means that our distribution shifts in the training process. So let's just have a look at it. So if this is our, I don't know, second layer of our model, and this is our third layer of our model. And we have here at the first step like a Gaussian distribution. This layer now learns that the input to layer 3 is a Gaussian distribution normalized with like a standardization of 1 and a mean with 0. The problem now is that the layer 2 also updates the weights, and this shifts this distribution to maybe something like this. And now this layer just has the weights trained for this distribution, so we have to update the weights again for this new distribution, and that's what the internal covariate shift is. And the authors find out if we do like a batch normalization, we can stabilize the training process, and we are not having this internal covariate shift. So it's not completely solved, but it's not so hard. And maybe let's have a look how batch norm works. So what we are actually doing, we go over a batch, so we have a batch size. We can say batch size is something like, I don't know, 32. And now we are adding for one neuron, so we are just looking at one neuron, and we are adding all the activations of the neuron in this batch together. So let's do it correctly like this. And this is our mean for this one neuron. And now we can calculate also the variance, and the variance is just like this. Minus y. So that's the right way. So this one is the variance. And yeah, so it's for one neuron, we we take the activations for all the batches and we sum them up in order to calculate the mean, and we also calculate the variance. And now for this neuron we take, for example, the first input, so the first batch, so first sample in our batch, and now we subtract the mean and divide it by the standard deviation, and then we do it for all the other samples in this batch. And then we are doing it not just for the first neuron in our layer, we do it for every neuron. So this is how batch normalization works, and maybe we can just continue with the paper. So since then many variants of normalization layers have been proposed for different networks, architectures or domains. Today, virtually all modern networks use normalization layers, with layer normalization, being one of the most popular, particular and dominant transformer architectures. So in transformer, everyone is using LayerNorm, or currently LMS get more and more famous. So LMS-norm, I think they are also saying it here in the paper. LMS-norm is actually the same as LayerNorm, but you're not subtracting the mean, you're just dividing by the standard deviation. So in addition to achieving better results, they help accelerate and stabilize convergence. So if we are using any normalization, empirically it shows that it improves our training process. As neural networks become wider and deeper, this necessity becomes even more critical. So why is it even more critical? Okay, as when we get more layers, it's the variance of our activations can get larger, and also the mean can get larger, and we actually want to have all the values standardized, because then the training is easier. Consequently, normalization layers are widely regarded as crucial, if not indispensable, for the effective training of deep networks. So this paper challenged these beliefs by introducing a simple alternative normalization layer in transformers. Our exploration starts with the observation that LayerNorm layers map their inputs to outputs with a tangent-like S-shaped curves. So let's maybe just dive into it, what they are meaning. We can see it in this picture. Okay, we now made a big jump, but here they are just talking a little bit about batch normalization. I already did this intro to you, nothing special. They are also saying something about LayerNorm, how it is calculated, but that's not so important at this moment. We can just have a look at this figure. So what we are seeing on the left side, we have different models. So for example, we have the VIT, we have wave to vec. So wave to vec is language model, VIT is for in the computer vision domain, and then we have DIT. DIT is for generative models, diffusion models. Okay, and then we have, like always here, the layer 5, and the more we get to the right, the layer is far more to the right in our network. So we have like layer 15, 20 and layer 25. And then what they are showing here on the x-axis, it's the activation of our neuron, and on the y-axis is the output after the LayerNorm. And what can we see here? We have like a linear function in the first layer. So if you put in, I don't know, 0, you will get out 0. If you put 1 into it, you can get a 1 out, stuff like that. So just a linear function, but no, yeah, everything is linear. So if we look now at the second column, we see it's changed, and it gets more and more a tanh-like function. We can see it here directly at the end and also here. So what is tanh-like function? It's like, it looks like this. It goes from +1 to -1, and yeah, a few years ago, we always used like tanh as an activation function, but then everyone used like ReLU, because ReLU goes like this and has like better gradients. If you're in this area, for example, you can have the problem of vanishing gradients, because the gradient here gets very, very low, and also here. Okay, so let's have a look again on this picture, and we see, okay, the more we can get to the right, the more the LayerNorm gets non-linear, and it's more and more a tanh-like function. Maybe we could also just read the description together. We sample a mini batch of samples and plot the input. So what we can see is it's like a batch. So it's not just for one activation. They sampled a whole mini batch, and one important thing is the outputs are before the affine transformation in LayerNorm. So let's have a look again what the affine transformation is. This one, so we scale, after we do LayerNorm or batch norm, we have two learnable parameters. Sometimes they are not even used anymore in some architectures in a large language model. And yeah, those are learnable parameters in order to scale the mean and add like a bias to it. Okay, and there in this figure they just looked at those values without the affine transformation. The S-shaped curves highly resemble that of a tanh function. The more linear shapes in the earlier layers can also be captured by the center part of a tanh-like curve. So what are they saying? They say that, okay, we have here like a linear function, and we also have a linear function in the tanh function. Let's just draw it again from -1 to 1, and we see this one here in the middle. We actually do have just a linear function. So it's possible to also do just a linear mapping if you use this tanh function. Okay. So in the chapter 3 they are actually saying everything we already talked about in this figure. So we can skip the most part of it, I would say, and we can just jump into part 4, where they are introducing now the new layer, and this one should be used instead of the LayerNorm. That's what the authors are claiming. So if you look at this picture here, we can see, instead of doing like the LayerNorm with the normalization and then scale and shift, scale shift is just this plus beta. So this is our mean or our calculated distribution, and then we can have like two parameters to scale it, and normalize is like the layer normalization, or you could also do batch norm, but if you have like in the transformer block, everyone actually use LayerNorm or RMS norm. So we can see this original block on the left, and on the right we can see the solution, or the idea that these authors are showing. And here they using the DYT, so dynamic function. Why is it called dynamic? Because this alpha is a learnable parameter, but it's just one parameter. So x is a vector, like this, and then we have alpha as one parameter. So alpha is just one dimensional and not, does not have the same dimension as x. Okay, so all dimensions will be multiplied by the same alpha, and this is what they're actually showing. And let's just jump back to chapter 4, and here we can see it, how it works. So we have x is our output vector, so our activations from the layer -1. So this one is layer L, and this is layer L -1. And now we have like activation 1, activation 2, up to activation n, and now we take all those values and multiply it by this alpha. So we have actually alpha 1, A1, alpha 2, A2, and so on, and alpha n, AN. So we have our scaled activations, and then what we are doing for each dimension, we just do the functions, so from 1 to -1. So if this input was very large, we also normalize it, because then we are more at the right side if it's very large, and the output value will be not large. So for example, our activation is 10, and 10 is far to the right, and then the maximum is like a little, it's 1. So not completely 1, but it's kept to it won't get larger as 1. And the same way, if we get really low values, so -10, we are here, and we also get -1 as the output. So we have a normalization for each dimension. And now the cool thing is the authors find out that normally we all the outputs in the layer norm were in this area. So what does it mean? Here we just have a linear function. So this is now this function works actually similar to the layer norm, but it brings some cool benefits with it. And the benefits is that it's now can be trained faster, because calculating like the mean and the standard deviation on the GPU is not so fast. So if we instead using just this tangent function, we are much faster instead of using the layer norm. I think they also have it here written in one table. Let's have a look where it is. Oh yeah, here we can see it. Efficiency of DYT. And what we see is, if they compare to RMS norm, as RMS norm is even if more efficient than layer norm. So layer norm has even higher values, and DIT is much faster, so it takes half of the time approximately here, up to half of the time as the RMS norm. So it's a pretty cool thing if we could just change all the layer norms with tangent functions, and that's what they did. And they show that actually at the end, if they compare it with other models, the results are similar and sometimes even better. Where can we find it? We can find it. Yeah, we can find it here, for example. So they trained a VIT base and a VIT large, and they show us the accuracy for image classifications, and they show that the DIT is a little better than the normal layer norm. So I would say we talked about the most important parts of this paper. If you want to read more about the experiments they did, I will put the link to the paper into the video description, and I hope we see us in the next video.